introduce them?
There are a few right now. I'll try to go dredge up some more. I say there's the room. We've got a couple members of the WAS here and an employee of Cranbrook. Hi, Nick.
Well, we still have a couple of minutes.
Pardon me? The map that we have at the desk is on the map. It is?
Morning. Oh, morning.
Good morning.
It's been a while. Hi, Father Riccioli. Nice to see you again.
How are you?
I'm fine. Haven't seen you guys since Rome, I think. I don't know.
That would be appropriate.
Yeah, exactly. Yeah.
Of course. That's where we bless Saul.
We might hear.
I think the year was 1617.
Maybe 1618. Let's see. I'll have to check my calendar.
Well, welcome everybody. We are now seated in many different places, including Bologna, Italy, because Father Riccioli is full of Bologna. And it will be our delight this week to speak with one of the great Jesuit astronomers of all time in a 1 day removed, 1 day and 1 month removed April Fool's Day event. The joke was on us because Father Riccioli couldn't make it. But I understand, we'll start telling people about the weather and what's going on. I understand there's a bit of a horse race happening where you are, Father Riccioli. And what's the weather like there?
The weather is cool, unfortunately, a little drizzly on and off. But the run for the roses in the Bologna Derby is will go on even if the jockeys all become covered in mud.
A little bit of mudslinging happening.
Yes. Yes.
Bob, you've got a whole room full of empty chairs and a few people. Tell us where you are and what that's all about.
I am at Cranbrook Institute of Science right now. There is a what's called Discovery Days. It's a public event. The Warren Astronomical Society is right outside that door with a whole bunch of telescopes looking at the sun right now. My wife is at the table with my meteorite collection, and she will have a gaggle of children around in front of her the entire day, because that's what happens when she's at these events.
Fantastic. So this is Cranbrook, which is in Bloomfield Hills, Michigan. And 2 miles from where I grew up. It's the science museum that I would ride my bike to on weekends because it was free back then. It cost a quarter to see the planetarium show, but the rest of the museum was free.
Wow.
Joel, where are you and what's the weather like?
Well, I'm down in Green Valley, 35 miles south of Tucson. Delightful weather. We've had a little bit of overcast things, but it's cleared up and in the low 80s, nice breeze, very, very nice weather, and perhaps good viewing for a couple of days.
I should point out that where Chris and I are is in Kennebunk, Maine, where it's in the low 50s and drizzly.
There's an autumnal crispness in the air that I noticed.
But it's Thursday of May. Come on.
Yeah.
Dennis, where are you?
I'm in Denver, Colorado, where it's sunny and low 70s.
Fabulous. Larry?
This is Larry Lebowski. I am 70 miles, give or take, northeast of downtown Tucson, Arizona, and about 1.5 miles higher than Tucson, Arizona, on the top of Mount Graham. It's clear-ish now. And if it cleared, it was after about 3:30 this morning when we gave up because of the clouds overhead. It's warmed up. It's 8 degrees centigrade now.
Fab, you're showing your age using centigrade instead of Celsius.
Well, that's what the reading says. I can't immediately convert it in my head. Sorry.
Celsius to centigrade? I think that's an easy conversion.
I see what you're saying. I thought you meant Fahrenheit. Sorry.
Rosemarie, where are you?
I am at the Jersey Shore, and it's about 55 degrees and cloudy. And I, too, am going to Monmouth Park to watch the Kentucky Derby this afternoon.
Oh, fabulous. Jeff, where are you?
Well, let me get this here. About 70 miles east of Manhattan. It's drizzly and it's about 52 degrees. And recently I saw M42. I took a picture of it. First one I ever did.
Fabulous.
So, but that's about it.
Okay. Paul and Linda, where are you and what's the weather?
Well, we're in Allentown, Pennsylvania. It's a little windy, a little cloudy, maybe a little sunny, maybe 65 degrees.
Okay. Katie.
Well, here in Pasadena, California, it's been cold, hot, whatever. It's 53 at night and 80 today, I guess, because the sun's coming out. I don't know. But I must say that lately it's been up. I was up at Mount Wilson last Sunday for a concert in the 100-inch dome, if I can just throw this in here. And it was 39 degrees in the dome. So the musicians were, but it was excellent anyway. It was so cold and foggy and windy up there. But it was a beautiful event. Sorry.
Excellent. Stanley.
I'm Philadelphia, Pennsylvania. It is 55 degrees and we're finally getting some sun through thick clouds.
Okay. Phil.
I'm in New Bern, Eastern North Carolina. It's cool and drab, and we're getting some much needed rain. But I did miss seeing the rise of the full moon last night. I always like to see that.
Gerent.
Hi, I'm in Swindon, England, UK, and nobody's perfect. According to my Google, it says I'm 5,238 miles east of you at the minute. It's 59 degrees Fahrenheit, 15 degrees Celsius, and it's about to be heavy rain.
Oh, lovely. I'm flying off to London and then on to Cambridge the end of this week. So
Oh, great.
I'll wave as we go past.
Thank you.
Juan Pablo.
Hi everyone, I'm in Phoenix, Arizona. Clear skies, 27 degrees Celsius because I'm also getting old. So all my measurements are in Celsius here. So beautiful day today.
Thomas.
I'm in Tottenham, Ontario, Canada, and it's 32 degrees Fahrenheit and it snowed this morning. So north of Toronto, 50 miles north of Toronto.
Right. I was just in Toronto last weekend.
I saw that after, too late. Yes.
David.
Yeah. Raleigh, North Carolina, it's rainy and around 60 degrees.
Okay. And Bill.
Hey, it's about 51 degrees outside in Batavia, Illinois. And the sky is clear with, the occasional cloud, so it's nice.
Very nice.
And I have the wrong face of the moon in my background picture.
Tom.
Hi, folks. Tom Cole, Philly, mid-50s, overcast.
Okay. Maureen.
Hi, I'm in New York, Manhattan. It's about 57 degrees Fahrenheit. New Yorkers don't do anything with Fahrenheit. We're a little slow in that department. And and it was overcast last night, so we couldn't see very much of the full moon.
And Justin.
53 degrees in Watertown, Connecticut, and lightly raining here. And it was cloudy last evening, unfortunately.
Okay.
Justin, your book is in the mail going down to Georgia, by the way. So
thank you.
Took care of that.
Okay. And Paul, tell us where you are and then tell us what's the latest on the telescope.
Well, greetings from Tucson. I have to say that the cool thing I've seen in the sky was the setting new moon, full moon, nearly full moon, yesterday morning after I dropped you off at the airport. It was very yellow. Anyway, the telescope, well, Larry is the one who is actually at the telescope observing. We are currently expecting some more observing runs before the end of the semester, but from the Northern Arizona University mainly. And the thing that has changed quite a bit, of course, is that employee who's been there for a long time as our facility manager, person who was there during the day, took care of things, and was really very reliable and dedicated and all that. He had a surgery Thursday before last, and he is in recovery now, and it doesn't look particularly optimistic as to him coming back. So that's kind of where we're at. The nice thing is that other people, other groups have pitched in to make sure that we can run, but yeah, it's tricky because commuting from Tucson to the telescope is just not really feasible. It may be, as Larry said, 70 miles, but that's the direct distance as the crow flies. In fact, it is. In fact, it is 3.5 hours or so to get there one way. So obviously, the employee who would be taking care of the facility needs to be based a little closer. So that's kind of where we're at with that. And believe it or not, the university still hadn't posted the job. It's stuck somewhere at the HR for reasons I don't understand. So anyway, hopefully it'll be sorted out sooner rather than later.
Well, I think one of the points to make is that the telescope is not only the equipment, but the people.
Right.
And we've been blessed over the last 30 years with some really excellent people. One or two duds, but I won't mention you by name. And we're very, very thankful for the people, and we miss them. We miss them when we leave. Gary has the marvelous name of Gary Gray, so it's used the same letters both ways, spelling it, which I always thought was amusing. I don't know what his parents were thinking.
Well, if they were anything like him, it was probably intentional.
Excellent. Anybody have any questions for Paul? We've missed him for the last couple of months. So questions about the telescope and how things are going. This is the chance to do it.
Oh, I just asked one question. What was the latest research that was being done at the telescope?
Well, research that Larry did.
The latest research that we're trying to do that is actually observed near-Earth asteroids, basically doing astrometry to get their orbits known better. And we tend to observe near full moon because nobody else around the world is observing near full moon because they're not crazy enough to do it. But we actually, on a good night, we'll get half a dozen or more asteroids to fill in the gap between the last time people observed and the next time most of the other people observed. Last night we had lots of puffy clouds, which kept us from actually doing anything, unfortunately.
So before Larry's run, we had Chris Corbally up there. He did two things. One was essentially a pilot project for yet another Chris. What's his name?
Christopher Bass.
Yes, there you go, Bass. So this is a gentleman from Lemoyne, correct?
Lemoyne College, where I'll be in the fall.
Right, and he wanted to see whether he could get some spectroscopic information on some asteroids. So Chris usually doesn't use a spectrum, our spectrometer in the way that Chris Bass wanted. So this was a kind of a pilot project. It's our differences anyway. So he took the data, and we shall see whether the customer, so to speak, is happy with it. Chris also did his own research, which has to do with stellar astrophysics. I don't quite recall which stars he was looking at, but he, throughout the run, basically had pretty bad weather. So it's wonderful that he managed to get what he did. The run before that, those were the people from the Northern Arizona University, and they were doing some active asteroids. So an active asteroid, the way I understand it in very layman's terms, is an asteroid that from time to time degasses. So it's gas and maybe a little bit of dust that puffs out of the surface of an asteroid, and you can see it if you have really very good seeing and a very sharp image. So the NAU people are very happy with Robert Crawford's gizmo called Donut, which Larry can tell us a lot about. It's a utility, a tool, if you like, that allows you to focus the telescope and collimate it in next to no time. And so every time they go to another field and they want to make sure that they are really, really in focus, the NAU people do a donut exposure, a couple of exposures, and calculate the correct position of the secondary mirror. So that was that. We also had an abortive attempt to train somebody from the Catalina Sky Survey, because starting next semester, the Catalina Sky Survey will be using the VAT several nights a month for follow-up observations. So the Catalina Sky Survey is, by many metrics, the most productive discovery machine for asteroids. And they discover the asteroid, but then they need to do some follow-up observing on the asteroid. And for that, they need telescopes. So the VAT got some funding thanks to the Catalina Sky Survey from NASA. So, all right. That kind of covers Stanley's question.
Great to have you here. And with that, and with the chimes of the church bells in Bologna, Italy, we now turn to our guest of honor. So, Father Giovanni Battista Riccioli, please sign in.
Hello.
It's great to have you here. Tell us a little bit about yourself. What are you most famous for, would you say?
I would say that I'm most famous for, in other words, if most known for my map of the moon. If I'm going to be known for something that a broad number of people are known for, it would be the map of the moon. I named the features on the moon, and most particularly, I named the Sea of Tranquility. So, when the Apollo astronauts landed, Apollo 11, and they landed at the Sea of Tranquility, I named that thing. So,
when was that you did that naming?
Oh, a long time ago, 300, 400 years. But I published the map of that in my Almagestum Novum, which was published in 1651. So I named it. I came up with the naming system sometime before 1651. I think maybe it was 1647. I'm not sure. That's a long time ago. I don't know how I'm supposed to remember that kind of stuff.
Well, just how old are you then?
Well, I was born in 1598, so you do the math, and I don't know what's that, 428 years old.
Fabulous. You don't look a day over 400.
No.
Marvelous. Where were you born?
I was born in Italy, and I grew up and went to school in Parma. That's I was and
it's a little town outside of Cleveland, right?
Yeah. It's Parma is between. It's down from, there's Milan and there's Cremona, there's Parma, Modena, Bologna. They all run along in the
sort of central northern part of Italy there.
Yes.
So
yes.
I notice you've got the letters SJ after your name. You were a member of the Society of Jesus, Societas Jesu. When did that
happen? I entered the society when I was 16. 16 years old. So that would be 1614.
Oh my
So
goodness, that was about the time that Galileo was publishing his famous books.
that is, yeah, that's shortly thereafter. He published that when he published his Sidereus Nuncius. I was like 12, maybe not even 12.
Did you read it when it came out?
I got the ebook version, you know, and so I skimmed it. You know.
What
I wasn't that much into astronomy at that time, but you know, everybody was talking about it. It had gone viral, so you know, you sort of had to look at it. So yes.
What was your family like? What was your family background? Were they fabulously wealthy?
No, you know, but it was all right. So I was able to, you know, get an education.
Okay.
And you know, I wasn't in poverty or anything.
So when you entered the Jesuits, was it your intention to become a world famous astronomer?
No, you know, I was like anybody else. I mean, I entered the Jesuits at 16. I was, you know, had sort of vague 16-year-old ideas about what being a Jesuit would be like, you know, save the world and, you know, go all over the place. I think I wanted to go to far lands or something like that. And I kept asking for that, you know, even after I gotten my education, you know, but they don't, just because you want to do something doesn't mean that that's what you get to do, you know. And
that vow of obedience is the hardest one, definitely.
yeah. So I ended up, I was just sent to my alma mater, and you know, I taught physics and, you know, basic stuff. And you know, I had originally set out, you know, I mean, you know, I would be in theology and, you know, sort of typical what you would think of as religious life. But I got interested in astronomy, and you know, I kept getting more, and I started pestering to do that more, and eventually was allowed to do that. And so, you know, it was Bianchini was at Parma. He had studied Galileo's stuff, and I got interested, and so astronomy was my life.
So, you know. What do you think of Galileo? Okay, he was a generation ahead of you, basically, made a big splash, and then 20 years later gets into trouble. What's your opinion? Oh, you're honest. You're among friends. It's not as if you're being recorded by, you know, for posterity here. Seriously, what did you think of Galileo?
Well, I thought, you know, I thought good things and I thought bad things. He, you know, his work motivated me in many ways. You know, for example, you may know I did some of the first precision measurements of gravity. And
tell us about that. Tell us.
Well, me and some of my Jesuit brothers started making up clay balls to drop out of windows of church towers in Bologna, and we I mean,
sounds like not a very safe place to be walking around.
Yeah, you definitely didn't want to be beneath us when we were doing that. But we, you know, we had multiple people we could keep, you know, keep people out from underneath. And you know, Galileo had talked about, for example, dropping a 100-pound ball off of a tower, you know, and the number he gave, like, we had dropped some stuff, and the number he gave didn't line up with our results, you know. So, like, I don't think he dropped that ball. You know, I think he just made that number up, and he's got something kind of reasonable. But nobody's going to go haul a 100-pound ball up a bell tower and then drop it. But we started, you know, dropping clay balls about half a pound, and we dropped solid ones, we dropped hollow ones, we dropped ones that were, you know, so they'd be the same, the same size but different weights. We'd have same density, different sizes, different weights. We dropped all these things. We dropped them. We went up to the top of the the Asinelli Tower in Bologna, which is 300 feet or more. If you go up the stairs of there, it's quite creepy. I'm sure it's even creepier now, 400 years later, but it's creepy enough then. And the tower was already 500 years old or something when we went up it. And you throw plumb lines down off of this thing and you drop balls, and you've got about 5 seconds of time. And the way we timed it is we trained. So we spent a bunch of time working on pendulums. What is it? Nicola Cabello. I had him up all night long counting the swings of a pendulum because we wanted a precise pendulum. And what do you got to measure time precisely? You set up a telescope. You aim it at a star. Set up a couple things, and you can time stars crossing some reference point, and that's your most precise time you get. Well, to time that reasonably well, you've got to have a pretty long span of time to do that with any precision. We had hours. So these guys, keep that pendulum going, keep that pendulum going. Just 24 hours, 8 hours, depending on which astronomical objects we were using, in order to get that timing right. And we time the pendulums, and we got a pendulum, then we time other pendulums those pendulums, shorter pendulums. So we got down to pendulums that would do 6 swings a second, and then we would then some of the guys who were good at music would sing in time with that pendulum. And by doing this, while the balls fell, we were able to time those balls down to a 1/6 of a second. And we had people at the top and people at the bottom, and we were both marking it, and we were in agreement every time. We got the precision of those drops down to a science. And we found out that, Galileo was wrong. He didn't drop the cannonball. It wasn't the time that he said, but his ideas were right, and so that's Galileo. Sometimes he's full of baloney. Sometimes he's great, and
I'm surprised you're able to say nice things about Galileo, and probably you have strong opinions about Copernicus too. What do you think of Copernicus?
no, that was, he also had good ideas, but the problem with these guys is, to make another joke, they had stars in their eyes, right? If you want to say this, if you're going to say that the Earth moves and everything that is involved with that, because if you're going to say the Earth moves, then you're going to have to go, re-explain all those biblical verses that speak about the Earth being fixed or solid or things like that. You better have your goods. And there's really, there's all these arguments. I went through 128, 126 arguments that people had made for the motion of the Earth, against the motion of the Earth, for the motion of the Earth, against the motion of the Earth. Most of those arguments, some of them were okay, some of them were just stupid,
Give me an example of a stupid one.
Oh, stupid stuff is like, I don't know. If the Earth is moving, well, I'll get dizzy or something like that. These kind of things. If the Earth is moving, how come there's clouds? How come they're not left behind and stuff like that? That's pretty straightforward, right? If the Earth is moving, the air is moving with us. We can figure this out. A little bit, better ones had to do with, the nature of physics. What is gravity? Gravity is the natural tendency of heavy objects to move toward the center of the universe. And so how are you going to have the Earth move? How do you justify a moving Earth in that regard? Well, you can come up with what Copernicus basically does. This is gravity is the tendency of earthly objects to move toward an earthly center. And then that center circles the sun. How, he doesn't have any idea, but he sort of puts it all into some sort of crystal ball that's carried around the sun on some other crystal ball. Okay, maybe that's true. All right, but it's hard to know. Whereas what we really come down to is parallax. If the Earth is going around the sun, then our views of the stars should change. They don't change. So the Copernicans say, well, the stars, they're far away. Yeah, that's it. The stars are far away. Yeah, far away stars. That's our answer to this huge problem with our system. And
how do you measure
I'm sorry, but Thomas Egan just put up a What Me Worry Mad Magazine picture, and it's totally distracted me. Hang on a minute. I'm moving that. There we go. So what was I saying? The parallax. Yeah.
Parallax. So how do you determine? Oh, wait for the town chimes to finish. How do you determine the distance to the stars? How do you know if the stars are nearby or far away?
Well, from Earth, that the moon shows parallax, for example. If you have two people who are separated by, several hundred miles, and they precisely observe the moon and measure its position relative to surrounding stars, you find that the moon's not in quite the same place for those two observers. And you can actually do this for yourself in one position, measure the moon evening, midnight, and morning, and you can see the moon shifting just due to your different positions on the Earth relative to the moon. So the Earth is not as a point with respect to the moon. The moon, and you can calculate, and we get I don't know what's the moon's 60 Earths from Earth radii away, and that's very reproducible, very easy to do. The sun, there's debate over the parallax and the distance of the sun. Everything else is pretty hard, and but it doesn't really matter, because the point is, if you don't, Tycho Brahe went through a lot of effort to measure parallax in stars, and he didn't succeed. And okay, that doesn't mean so he doesn't determine how far the stars are away, but he knows how far away they would be for him to detect them, and therefore the stars must be further than that. And he gets hundreds of times further than Saturn. There's this huge distance, the Copernican system. Well, the problem with this is that you look at a star and it's got a size, and so its absolute size is a combination of how big it looks to us and how far away it is. So the further away the Copernicans make the stars, the bigger they got to be. And
what's this? You mean the stars have a size? When you look at them in a telescope, you actually see a little disk?
Well, first, when you look at them with your eyes, you see a disk, right? Look up at the sky. If you got good eyes, now people who have bad eyes, they see a little fuzzy ball. They'll say, but if you have good eyes, you see little round dots. And you ask people, how many of those little round dots does it take to cross the moon? And they'll come up with, 20, 30, 40. This is a hard thing to measure. But, so let's say they're, a 20th the size of the moon. You see them with your eye. Well, that means that if they were the same size as the moon, they'd have to be 20 times further away than the moon. Okay, if they look a 20th the moon's diameter, and they're the same size as the moon, they go by 20 times away. So, you do this for the stars, and they come out to be, the distances, if they're going to be the distances Copernicus says, they're bigger than the whole universe, right? The Tycho Brahe calculated you got the Earth and you got the planets and stuff going around the Earth, and then you have the stars out past Saturn. And Johannes Kepler calculated that the nova of 1604 was bigger than the whole planetary system together. So anyhow, these stars have to be huge, and to be at those distances. So the Copernicans, they're just making stuff up, right? They got a problem. Their problem is we see no parallax. Well, they're far away. Well, that makes them huge. Well, okay, they're huge then. They're huge. God is great. God makes huge stars. Yay for God. This is the Copernicans' answer to a problem, and okay, you get a telescope, and for a minute there was like, oh, this is going to, no, you look through a telescope, you see a disc. Actually, what you'll see is you actually see a disc, and it'll have some rings and stuff around it. But if you focus the telescope and constrict the aperture down, you get rid of that junk and you can see just the star. And you do this, you consistently get results. The problem with the telescope is it makes the parallax measurement more precise. So the telescope actually shows us that the star's a little smaller than we thought, but you have to make the stars further away because of that. It still comes out in the wash. You still got stars that are the size of, bigger than the orbit of Earth.
I understand that Galileo claimed the stars were 2 1,000 times farther away than the sun.
Yeah,
Obviously, an absurd distance.
yeah. None of it's not enough. It's not enough. He claimed that the sixth magnitude stars are that far away, but he gets the brighter stars are even closer, and that's not far enough. If they were that distance away, we would be able to get their parallax. They're further.
Measuring whether or not the Earth spins. I understand you've got a clever way to prove that.
Yes, there's a variety of things. If the Earth spins, then okay, it's not. People will say, oh, Galileo said like, oh, Tycho Brahe couldn't get it into his head that if you drop a rock from the top of mast of a ship on a moving ship, that it'll hit the bottom. That Brahe thought that it would fall, that it would stand still and the ship would move out from underneath it as it fell. And that's Galileo at his worst. Okay, that's Galileo taking something that Brahe knew and twisting it around. Okay, so Brahe's view was that a cannonball, something you dropped had impetus, and it would fall, but it would lose some of that impetus, so it would fall behind the mast a little bit, maybe. Okay, but even if we take the a view of impetus that something will just keep moving, okay, so that if you drop the rock at the top of the ship, it just falls straight to the bottom like the ship wasn't moving. Well, the Earth isn't a ship. Okay, if Copernicus is right and the Earth is spinning, then the poles are hardly moving at all, and the equator is moving at a very rapid rate. So if you are at the equator and you shoot a cannonball to the north, the cannonball is going to be moving faster than the northern ground that it covers, and so it's going to deflect. Okay, we don't detect any deflection.
Right. We've never seen a cannonball veer off to the east.
You never see a cannonball veer off to the east. There are regular reports that there are gunners who can drop a cannonball into the mouth of an enemy's cannon at range. This is reported by multiple military people. If this happened, there would be reports in the military that you can only do that if you shoot east or west. You can't do that if you shoot north or south. Furthermore, you can drop things. We dropped a lot of balls. If you drop balls, they should deflect. We didn't detect any deflection. We spent a lot of time messing with pendulums. You would think that if the Earth is turning and all this, there would be effects on the pendulum's tendency to seek the center of the Earth. You would get some variations in the period of the pendulum. We saw no effect in the pendulum. We saw no effect in the periods. We saw nothing at all. Now, maybe these effects are even smaller than we think. I don't think so. But the problem is on the Copernicans. There's no evidence for their system. And they have to have giant stars and attribute it to the power of God in order for their system to work. Now some of them are happy with that. Johannes Kepler, man, he just thinks that big stars are God's testimony. So Philip Lambergen. I find, you can't deny the power of God, but I just feel that such arguments don't satisfy the more prudent kind of person.
So I understand then you've got this opinion that Copernicus must be wrong and Kepler must be wrong and Galileo must be wrong. So when it came time to make your map of the moon, what did you do with these guys?
Oh, these guys are good. They're wrong on this. They're not bad scientists. And I put them. I started the moon map, and I sort of started with the ancients and went around to the moderns. And their contributions are worth acknowledging. I have a big crater. I've named the biggest crater there for Tycho Brahe. I think but Copernicus, Galileo, and Kepler are all worthwhile people. I also named it for many of our Jesuit brethren are named on that map, but I put them on there too. I put Kepler and Galileo and Copernicus on there too.
So what was the reaction when you published this big book? What was the name of the book again?
Almagestum Novum.
And where did that name come from?
Well, Ptolemy wrote the Almagest, which was the standard, that was the source of all astronomical knowledge for 1,500 years or so, but I'm aiming to supersede that. And so this is the new Almagest. And it's big. It's about 1,500 pages, full size, like this.
Fabulous. Well, we've got some questions here.
Okay.
Father Riccioli, what kind of instrument did you use? You made this fabulous map of the moon, which is, to look at it, even 400 years later, we recognize that's the map of the moon. It's as accurate as anybody we could imagine, and any amateur could do. What was your telescope?
It was a telescope. We used a variety of telescopes. So a little bit better probably than what Galileo had, because we're now talking 60 years, not 60 years, how many, whatever. It's been a long time, 30 years later, than from when he was doing his stuff. But you would recognize it, lens at one end, lens at the other. Aperture usually being constricted down to half an inch or an inch to get the best part of the lens and to shave off all the glare that you get, especially when you're looking at small objects. When you look up at the sky at Venus or Jupiter, it looks like a round dot. And, you look at it with a telescope, and the telescope shaves off the glare so that when you see Jupiter, you see it's got moons, it's got little bands on it. You see Venus, it's got a phase, right? So that's one of the key things that a telescope does, is shave the glare off of things. But if you by shrinking down the aperture of the telescope, you can get the best part of the lens, and you can shave off that glare, get your best view of stars. But it's a standard 2-lens telescope is what we use. And then other quadrants and the usual non-telescopic instruments. But for the moon map, that was a telescopic study.
Now, remember that you named a crater for yourself, but also for a fellow named Grimaldi. Tell us a little bit about Grimaldi.
Yeah. Oh God, what my right-hand guy. He was he basically. He's the guy who worked out the physics for the deflection of the cannonballs and what sort of a trajectory that they would follow if the Earth was turning versus what they actually follow, and things like that. He was brilliant, always willing to work. A lot of those guys I worked with, just I couldn't ask for a better bunch of people. How many people can you get to sit and count a pendulum, for 8 hours in a row? They're just, and Grimaldi, he much of the work that's in the Almagestum Novum is owed to that young man. So he needs to cut his hair more often, though, as I'm always telling him.
I will point out that my name is Guy. I was named for my uncle, Guido Grimaldi. So,
oh, really?
I won't claim that he was a direct descendant, because Grimaldi was a Jesuit priest, but still, I'd like to pretend there was a relationship there.
Wow.
This is my uncle by marriage, so I can't, claim blood either. But I understand Grimaldi did some work with waves and diffraction. You're familiar with that?
Yeah, he is. Actually, I'm not. I'm pretty sure he did that after I died.
Oh, okay. Very sad. And someone else is asking, what did the Pope and your religious superiors think of the work you did, the book?
I think the book that I wrote is the book that Pope Urban wanted Galileo to write. I think that he wanted to, that's so, in the end, my book became sort of the standard reference in my arguments. My arguments are not just my arguments. For example, Father Scheiner and his student Johann Georg Locher, they wrote a book in 1614 with much of the stuff that I talk about, just in less detail. They offer a very succinct illustration of the problem of the star sizes. They just say, I have all these measurements and calculations, all this. They just say, look, in the Copernican system, the Earth is a point, whereas the stars we see up in the sky are not points. Ergo, in the Copernican universe, the stars are bigger than the orbit. The Copernicans say the orbit of the Earth is a point. The stars in the sky are not. Therefore, they're very small, but they're not points. You can measure them. Therefore, The stars are bigger than the orbit of the Earth, right? That's a very succinct summary of the objection of star sizes to the Copernican system. He also they actually did they worked out a physics for how a falling object would work on a rotating Earth. So they actually worked around the physics problem for the Copernicans, but you still have the problems of falling bodies and all these other things. So people are willing. We've always been willing in the Church of Scientists to study these ideas and see where they lead. The problem for Copernicus and Galileo is they don't lead in the right place. They lead to absurd ideas about the stars. They lead to expectations of physical phenomena on the Earth that don't occur. And do you expect that, then you're going to go and say, well, we need to reinterpret scripture for your pet idea. You're going to go throw people into tizzy for something that's not been confirmed. You can't do that, And so it was right for him to have been, for Galileo to have been condemned. He was taking his own ideas and walking off into stuff that's could cause real trouble if he was wrong, which he was.
The bells have chimed, and at this point, our Ouija board is no longer able to communicate with the 400-year-old Riccioli. So, Chris Graney, if you can remove your magic hat. And now speak to us as a scientist of 2026.
Huh? What? Where am I? What am I doing? What? Oh, I've got head hair.
Tell us of where did Riccioli go wrong in the measurement of cannonballs not veering off?
He just wasn't. The measurements were just harder than what they thought. And it's true. They did think, when in discussion of this, there's the thing from, I think it's Christopher Wren, who designed the St. Paul's Cathedral. There's actually a recording in one of the meetings of the Royal Society where he's like, yeah, everybody knows that, the gunners know the right angle to shoot a cannonball up in the air and have it come back down and fall right into the mouth of the cannon. Like, they had these ridiculous ideas about how accurate their artillery was. This must have been like a joke that the military people like to say, oh yeah, we can do this. And of course they couldn't. And so the experiments were just a lot harder, and nobody knew about things like turbulence. And you would think that if you just drop a heavy object from a high place, it'd fall down to the place it's going to fall. But it turns out as it gets going, you get all these turbulence effects on it, and the ball starts doing this on its way down. And in fact, you get, the balls won't land in any kind of consistent pattern. And, so it's just really hard to do that experiment.
It's like like a baseball. It's, if it's got any kind of spin, it's going to go off one way or the other.
Yeah. And if it doesn't have spin, that's a knuckleball where the ball's like doing this. So it was just a much harder thing to do. And it turns out he was right. And so there's a guy, another Jesuit, Deschales. He has these beautiful illustrations that could go in a modern textbook of the Coriolis effect. But his whole point was these were arguments against Copernicus. Eventually, the effect was detected and it was real. But so they were right. And they were right that you couldn't detect it, but their conclusions were wrong. And the stars was due to the issue of diffraction, which someone was asking me about. I think that was after Riccioli died, but Grimaldi is actually the one who discovered the effect of diffraction. I don't know. That's a good piece of research because there's plenty of history of science research for somebody who wants to do it. But was Grimaldi led to that by their efforts at measuring stars? Because eventually what happens is there's two things. Christian Huygens comes up with the idea of it's reducing the glare of stars and stuff in telescopes, not by constricting the aperture, which is what Riccioli talked about and which was the standard thing to do, but instead to put a piece of smoked glass in the optical pathway of the telescope. And then he finds that when you do that, the stars just fade down to points. They don't produce a consistent, because a diffraction pattern is a consistent thing. And if you shave off the extra rings on it, you get a consistent size. So if you did it by restricting the aperture, you got a consistent result. But by smoking the glass, you didn't. And then that begins to lead to the realization that, and watching the moon pass in front of stars leads to the realization that those star sizes are spurious. And that's how the star size problem goes. But it's not until the 18th century, not until almost 100 years after Galileo dies. Forget about his condemnation. It's 100 years after Galileo dies, you have still got skilled astronomers reporting on diameters of stars and calculating that their sizes in the Copernican system have to beat that of the orbit of the Earth.
One of the other ironies is that, in fact, we do know stars that are bigger than the Earth's orbit of the sun. They're not all that common, but it's the other thing people didn't appreciate, that stars come in such a range of sizes and brightnesses.
That's right. That's right.
One last comment here from Gerard, the fellow named Michael Paskowitz, he lives about 30 miles from him in Gloucester, has talked about the Almagestum Novum. You've had contact with him, right?
Yeah, he's working at he's been working at translating it. He translated all like the introduction, 100 pages or something, of it. Of course, that only leaves 1,400 pages to go. Yeah.
One of the things that you and he are spectacular at is you're the first people to go back and dig into these works with a knowledge both of Latin and astronomy, so that you can recognize what they're talking about, even though they obviously don't have the modern terminology for it.
Yeah, and they're good. I have to say, I mean, one of the things is that once you start reading their stuff, it's like, these guys are good astronomers. They don't know what we know. But when you read the stuff that they're doing, it's not like, Galileo made fun of Christoph Scheiner's book that he did with Locher, that Father Riccioli referenced in 1614, and painted it like it was a joke. You go read it, it's not a joke. It's actually very sensible. These guys were sensible. They didn't know what we know, but their objection to the Copernican system was, reasonable. If you were alive then, you wouldn't have believed Galileo either. It's
which is a lesson, I guess, for all of us here. Thanks a whole lot. Before you leave, can you plug your latest book?
My latest book? Oh, gee. Well, let me plug my older book. If you want to know more about Riccioli, this is Setting Aside All Authority. Giovanni Battista Riccioli and the Science Against Copernicus in the Age of Galileo. And the current book just out this year is A Universe of Earths, Our Planet and Other Worlds from Copernicus to NASA, which has quite a bit in it about Kepler. When I did this book, this is 2015, I did not realize that Kepler was an enthusiastic giant stars Copernican, and who did all the Copernican things. He claimed that there was illustration of God's power and all that other stuff. He also used it to argue against Giordano Bruno's claims about that the stars were other suns orbiting other Earths. There's been a review of this book out in the journal Astrobiology, and the guy had a thought I wish I had thought of. And he said, the guy gave a pretty favorable review, and he pointed out that the Kepler mission to find exoplanets is named for a guy who believed that exoplanets didn't exist. And it's true. It's true. Kepler did not believe exoplanets existed because he believed that stars were giant objects, not like the sun. So they weren't suns. They weren't going to have planets around them.
I noticed a couple of bits from Bill Higgins. First, noting that Christopher Wren had the map maker make the first lunar globe. And also, he endorses that book, even though it's in audio form, an astronomy book without pictures. Any other questions from anybody in the group here? This is your chance to talk either to Riccioli or his avatar.
Yeah, I have to put my hat back on.
Hearing none? Oh, yeah, okay, yeah, Justin. Oh, he says no, okay. Thanks to everybody for joining us. I apologize that the full moon meetup was the day after the full moon. I was on an airplane during what this time would have been yesterday, which is why we couldn't do it then. And we apologize not having it on April Fool's Day as we planned, because Riccioli's avatar had wound up in the hospital. So,
not the hospital, just the urgent care center.
Urgent care, right.
Eye injury.
Great to see all of you, and look forward to see you all again a month from, well, one full moon from now.
28 days. Thank you, everybody. Thank you, Chris.
Adios.
Thank you. JP Del Toro, how are you? It's good. Oh, he left. No, I didn't.
Thank you.
Doing okay. Doing okay.
Are you wearing pearls? They're quite striking.
Am I wearing what?
What do you
pearls.
think?
It looked like you were wearing pearls. Sorry.
Oh, no. It's
Okay.
no.
Sure.
It's not pearls.
Okay. Oh,
It's
I see.
shells. It is shells.
Oh, okay. For a second, it looked like pearls. They look quite striking.
No. It is shells. Yeah.
Oh, okay.
Thanks, Bill, for joining us and the great comments you gave us. So hi to everybody at Cranbrook.
Hi, Bob. How are you, Bob? Hi, Bill.
And thank the images you sent. Those are spectacular. Okay, I got to get ready because I'm giving a talk in half an hour.
And I've got to eat my lunch.
All right. See everybody later. Bye.
Bye.
Bye.